Hey folks, this is Dr. Ayad. I'm going to be recording another homework help video for you all. This time we're going over the balancing chemical equations assignment. I've copied a few of the different problems over here, so let's dive right in. The purpose behind an assignment like this is figuring out how we're supposed to add and remove coefficients to these different chemical compounds in order to balance a chemical equation. Now, what is a balanced chemical equation? In science, we know that matter cannot be created, nor can it be destroyed. And the same thing applies in chemistry. So if we're saying that we add one S8 and one O2 to produce one SO2, well, something doesn't quite line up there. What we're saying is that 7 of our sulfur atoms disappeared in this process. A balanced chemical equation is one which has the exact same number of atoms on the reactants side as it has on the products side. In order to balance these equations, what we do first is we take a look at the subscripts for each of the different elements and figure out a number of coefficients we can add in front of those different compounds in order to make the exact same number of atoms on each side. There are a few different tricks and techniques that you can use for these. They're all pretty much interchangeable, but some are more situationally useful than others. On this first slide, I've collected all of the problems that have oxygen as one of the main reagents. The reason for that is we have a special technique when using oxygen in these reactions that makes some of them easier to solve. For the first one, though, it's pretty straightforward. And we're going to use an approach that I call the ping pong method. The reason it's called the ping pong method is because you're going to take one compound and you serve to the other side and you see if the elements are balanced. And if they're not balanced, then you go back over to the other side and you add something to balance it, and then you just go back and forth, and eventually it kind of solves itself in this way. So to start here, S8. All right, I'm going to serve over to the SO2 now. There are not 8 sulfurs yet. So how can I fix this? Well, if I multiply the number of SO2 compounds by 8, that would give me 8 sulfurs. So let's go ahead and write that in here. Let's see here. So we'll have, oh, goodness. Don't know why that happened. Hang on. So we'll have 8 sulfurs. Okay. But that doesn't completely solve the problem, does it? Because even though I have 8 sulfurs, and that's fine now, the number of oxygens has changed. So 8 times the 2 oxygens means I have 16 oxygens over here, and you can make a note of that. Notice that I'm writing oxygen atoms, not O2. We're trying to balance individual atoms here. So in order to balance those 16 oxygens, we serve back over to this side, and I have O2. Well, in order to make 16 O's, I'll need 8 O2s. And so I put an 8 coefficient there. And that's really all that's necessary in this one. The S8 is balanced here because we have 8 S's. The O2s, we have 16 of them, or 16 oxygens here, and O2 times 8 is also 16. And so we are finished. In the homework assignment, you're going to be given these boxes. Because of the way Luminome is set up, make sure you include 1s anywhere that there would be a coefficient of 1. You'll note, though, that when I looked over here at my PowerPoint, that I didn't write the 1 in. In general, 1s are understood or implied in chemistry. That's just not the same for this assignment. So we're going to put a 1 there, an 8 here, and an 8 there. And good news, I get to keep my job. Okay, let's move on to the next one. Now, this is a type of problem we call a combustion reaction. Combustion reactions in general are whenever you combine a hydrocarbon, that is something that is made up of primarily carbon and hydrogen, with oxygen in the presence of heat, and it's going to convert into 2 new compounds, CO2 and H2O, carbon dioxide, and of course, water. What makes these problems tricky is the oxygens, because we start with O2, and then it's somehow supposed to come over here and make 1, 2, 3 oxygens. What I'm going to have us do is balance everything except for oxygen, and then we balance the oxygen last. And there's a little trick for the balancing of the oxygens. So to begin, I noticed that we have 1 carbon and 1 carbon. So that's all balanced. What about the hydrogens? I have H4, H2. So I need twice as many hydrogens, and I take care of that by putting a 2 in front of the H2O. Now the carbons are balanced, the hydrogens are balanced, and the only thing that's not yet balanced are the oxygens. I'm going to put every oxygen atom over 2 here. The reason I do that is because we have O2 as our starting material. And so this is just going to clean up the number of oxygen atoms and convert it into oxygen molecules when we factor that denominator in. So I have 1, 2 from the carbon dioxide, and then 2 times 1 gives me another 2 from the water. That's a total of 4 oxygens. And, of course, 4 over 2 will simplify to 2O2. Oof. Still getting used to the tablet, sorry. 2 O2s. And so this would be a balanced reaction now, because we have 1 carbon, 4 hydrogens on both sides, and then 4 oxygens. This next one is a little bit trickier, because notice that we've included 2 oxygens on our hydrocarbon. That's totally fine, and the method will still work. We're just going to have to consider that we don't necessarily need to put all of the oxygen atoms over 2. We're going to put the oxygen atoms we don't yet have over 2. Let me show you. So I'm going to start with the 2 carbons, which means I need 2 CO2s. 4 hydrogens means I need 2 times 2 for 4 hydrogens. I'm going to count up the oxygens that I have over here now. 2 times 2 is 4 oxygens. And 2 times 1 is 2 oxygens. And when I add those together, I need to get 6 oxygens on my reactant side. So you might think of starting by putting 6 over 2. However, we already were given 2 oxygens in that reactant. In order to make this work, I'm going to subtract 2 oxygens from what I need. And so then when I simplify this out, we'll end up with 2 O2s. And so there's your answer. Let me just confirm that I got that one right. We had 1 of those, 2 of those, 2 of those, and 2 of those. Great. Moving right along then. These are reactions that we call either single displacement or double displacement, depending on whether one partner was swapped or both partners were swapped. Here in the case of aluminum and silver nitrate, the nitrate polyatomic ion is leaving the silver and going to the aluminum on the reactant side. In the bottom case, we have potassium nitrate and carbonic acid. They swap both partners. So the hydrogens end up going with the nitrates, and the carbonates end up going with the potassiums. Both of these are best solved through that ping-pong method I was mentioning earlier. Let's watch. So I'm going to start with the aluminum here. We have 1 aluminum on both sides. Okay, wasn't a great starting point. What about the nitrates? So I'm going to check out my nitrates. It looks like I have 3 of these. Notice that I'm talking about nitrate as if it is one complete entity. That's because polyatomic ions tend to stick together. They're not going to rip off nitrogens and oxygens. It's much more convenient for them to move around in this grouping. And so I can consider this as if it is one unit, which will make balancing a little faster. So I notice that I have 3 nitrates over here, but only 1 nitrate over here. I can fix that by putting a coefficient of 3 in front of my silver nitrate. Now I need to balance the silvers, so I serve that ball back over to this side, and so I need a 3 in front of that silver. Just to confirm, I'm going to go back through and check my work. Aluminum and aluminum. I have one of each of those. I have 3 silvers and 3 NO3s and 3 NO3s. In this case, the 3 coefficient with that nitrate means the same thing as the 3 subscript with that nitrate. And so there's our balanced equation. Moving on to the next one, I have potassium nitrate and carbonic acid. Fun fact, carbonic acid spontaneously decomposes. It is not a particularly stable molecule. And when it decomposes through this equilibrium reaction, it becomes H2O and CO2. This is the reaction that makes soda fizzy. You'll notice that in a 2-liter of Coca-Cola, when it's left undisturbed, you don't see any bubbles. But as soon as you shake it up, disturb it, open the cap, anything like that, it upsets the equilibrium and it causes this reaction to proceed, making water and the carbon dioxide fizz. Okay, sorry, just a fun fact. Moving back over here. I'm going to check out my nitrates. I got 1 nitrate and 1 nitrate. So far, so good. I'm going to check out my hydrogens. I've got 1 hydrogen here, but 2 hydrogens there. In order to fix that, I'm going to have to put a 2 in front of the HNO3. Now looking at that nitrate on the nitric acid, I know that I have more of those, so I bounce back over here, and I've got to put a 2 in front of the potassium nitrate. That's going to change the number of potassiums, so I'm going to check back over here. I've actually already got K2 there. We haven't talked about the carbonate ion yet, CO3 and CO3, so that's all balanced. And I think this is another finished equation here because we have 2 potassiums, 2 nitrates, 2 hydrogens, 2 carbonates. Move into the next one. This might look a little alien at first because it is a new type of reaction for us. This is what we call an acid-base reaction, and it technically has its own way to solve it. The prototypical acid-base reaction involves a hydrogen ion being combined with a hydroxide ion in order to form water, H2O. The positive cancels out the negative, and we end up with this neutral compound. And that's what's really happening here, that we have 3 hydroxides and 2 hydrogen ions, and they will combine together to make water and a salt. Now, the way chemists use salt is a little bit differently than the way you've probably used salt. We mean just a ionic compound, pretty much. Anything that can easily dissociate in water. In order to solve this, what we're going to do is we're going to separate out the hydroxides and the hydrogen ions first. Balance those according to this reaction equation, and then we'll stick those coefficients back onto their parent compounds, and it should solve things a little bit more quickly for us. So let me show you what I mean. The aluminum hydroxide is going to dissociate. Still getting used to that tablet, sorry. The aluminum hydroxide is going to dissociate into 3 OH minuses because we had a subscript of 3 here. The hydrogen from H2SO4 will dissociate into 2 H pluses. Now, how am I going to balance the 3 and the 2 here, and how many waters will it make? Well, it goes in a 1-to-1 ratio here, where for every 1 hydroxide, you should get 1 water. We can't just add one hydrogen because these ratios are absolute. They're based on the original compounds. So we have to find the lowest common factor between 3 and 2, which turns out to be 6. So I'm going to treat this like 2 times the quantity 3 hydroxides plus 3 times the quantity 2 hydrogen ions. And that should produce for me 3 times 2, 6 H2Os. Back up at our original equation, we're just going to apply those same coefficients here. So I've got 2 aluminum hydroxides, 3 sulfuric acids will produce probably one of these. We'll go back and check our work later, and 6 H2Os. To check our work, I'm going to look at those other ions and make sure they line up with this compound. Well, the 2 aluminums is 2 aluminums there, and the 3 sulfates, look at that, 3 sulfates right there. And so we know now that this is a balanced equation. Okay, thank you so much, folks, for listening. I hope that you found this instructive. Please email me with any questions that you have. Have a great rest of your day.